Okay, guys, what are sensors? Physical stimulus. We've got to stimulate it, right? Not just necessarily a physical condition. Capable of responding to physical stimuli, a device that converts a physical stimulus into electrical equivalent. Transducer, this is a device that converts one form of energy into another, which is basically, so you'll hear people call these things sensors, you'll hear them called transducers. Those two terms are used interchangeably. So you okay there? So what are some of the things that we might want our robot to sense? Yeah, but what in the surroundings? I mean, what can it sense in its surroundings? I mean,
how far something another
okay.
object is from it.
So distance. No, we're not reading. I mean, you can read. What we're trying to do is we're trying to come up with what we think the robot can sense. So what do you sense? What's some of the things you sense? Light. Okay, so we might want it to sense light, yeah. Might want it to sense sound. Might want it to sense heat or temperature. Well, what else?
Danger, but I don't think it could. Like,
well, we have to sense something else. So distance or drop off or stuff like that. So we can't sense danger. It's just like you can't. How do you sense danger? You use your senses, right? You understand that. Either your sight or your sound, right? You understand. So we don't sense danger.
I guess it's touch.
Touch, yeah. Touch is a good one. What else?
Overheating, I guess
that's temperature. Obstacles. Yeah, presence would probably. What about? We might want to sense like color, right? Might want to sense pressure. That would become very important, like in gripping applications. You know, I wouldn't want to put the same pressure on a chunk of metal that I do an egg. I want to sense moisture.
It does say flow here. Does that mean like energy?
No, flow is the movement of fluids. So how fast does fluid moves? So we're trying to sense the flow. You know. So that would either be the flow of gases or the flow of liquids, right? A lot of people get in trouble down at the beach because they don't sense the flow. Or they don't heed the riptide warnings, right?
It also says strain. Does that mean when it goes too much? What does that mean with strain?
Strain would be something that we stretch or put a force on to cause it to change shape. Yeah, position. Position that's a very important. We do that all the time. If I don't know where something's at. Or just knowing when something's there, like that robot up there. Right now, it knows the exact position it's in. Even though the controller's turned off, the robot has what we call encoders on there, and so the robot knows where it's at. Well, no, it's just where it's at. So the robot can't do anything about it, right? You understand? Because it's controlled by a controller. So what's some of the things? Pressure, level, distance. We already said that. What? Speed. We need to be able to sense speed, because if I'm doing things that speed critical, like welding or something like that, wire welding, then I got to go at a certain speed. And that's one of the biggest things, one of the things people have problems with while they're learning how to weld. Because unfortunately in today's society, we want everything yesterday, right? So, we get upset, huh?
With welding, it has to be precise.
You go too fast, you sputter a lot, you go too slow, you cool, you make your metals get too hot. If you're doing thin metals and you go too slow, you will literally melt through the metals, so it's very touchy. Speed, angle, feed rate, there's a lot of stuff you do. We might want to sense, we sense this, we have the ability to sense color, so there's a difference between light and color. We call it U or HUE or grade scale. There's a lot of robots that can't see color. We have two different types of, we call them cones and rods in our eyes. One of them senses hues. One of them senses shades of gray. And then we have red and blue and green. I get them confused, rods or cones. I don't remember which one. One of them senses color. One of them senses shades of gray. And so that's the way we see it. That's the way these monitors work, by the way. They got 4 colors available on these monitors. What do you think they are?
Primary color. Red, blue, green.
Well, and black we can't do. So that's the 3 things: black, red, green, and blue. That's it, guys. That's what your eyes can sense. So black, we call it shades of gray. It's the intensity of the black, right? You understand that? And then we combine those 4 colors, then we can basically do almost anything. We could do that toxicity. We could sense viscosity, the thickness of a liquid, viscosity. We might need to sense that. Flow, speed, it's all kind of stuff that we might want to sense. And what you got to understand is odds are there is a sensor out there that we can hook up to a robot, or that we don't hook it up to the robot. What controls everything that the robot does? Yeah, that's his brain right there. We called it a controller. So that's the controller. So the heat robot, which is pretty neat. The heat book robot, they refer to it as the brick, but this is the controller on the, on the Lego robot. This is the controller. So everything that I do is controlled by this controller. It can handle 4 different sensors. So that's on the bottom. These are where the sensors can go. And then it can control 4 outputs. This is where our servo motor is. I'm sorry, 3 motors. Well, it actually controls 3 outputs. We don't have these motors by default for what it considers to be, unless we tell it something different. It considers these ports right here to be motor ports, servo motor ports. And the ports on the bottom are for input or output. Most people generically call it out. So right now, these switches, I have the switches connected up. So these are sensors. So these are 2 sensors right here. Some people call them tactical sensors, which I can use. This is all done. It looks like this is a radio control car, but it's actually one controller that's been programmed to run this robot. Man, we're not programming with it. We're jogging with it. So basically, we're jogging with this. To be a true teacher, you have to be able to teach the program. I noticed a while ago on that point robot, that's what I was doing. I was teaching a program on a continuous path. I don't even know. I don't know what the pendant. If it's got a pendant, I don't know what they would call it, because you're not teaching at the pendant. You're teaching at the.
Well, they're basic control controller.
Yes. But they're actually computers. They're specialized computers, or they're basically computers that can control a bunch of inputs and a bunch of outputs. So the KUKA runs Windows XP. When you boot the KUKA, you'll see it comes up and shows that Windows logo when it pops up there. All the robots use proprietary operating systems. But let me erase this, and we'll look at, these are just some things that the other classes have come up with. So speed, position, speed, weight, count. We count all the time, right? Pressure, flow rate, temperature, light, thickness of solids, time, gas levels, distance, motion, orientation, how it's oriented or how it's shaped, proximity, moisture, and viscosity. But there's more, these are the things that we see, right? Plus other things that are not listed in here. Equilibrium. You say that. Equilibrium, which is our ability to, to stand upright and all kind of stuff. So we got all types of stuff that we can sense that people don't understand, that are not. So we say, what are our senses? A lot of people say, we got sight, we got hearing, we got smell, but we got a lot more than that. We can sense equilibrium, we can sense pressure, we can sense heat, or temperature. So we got a bunch of different sensors available. So the first sensors that we'll talk about, I think, in the textbook are distance sensors. So we have ultrasonic sensors. We got one of these over there on the Amatro line. And ultrasonics is considered to be frequencies of above 2,000 hertz. Don't understand those terms?
Hertz?
Yeah.
I'm just learning it.
What we do is when we send out, like Alabama Power generates a type of current called AC. It stands for alternating current.
I know that AC is kilohertz.
So what happens, the direction of current flow depends on the polarity of the push. So if this is a polarity of 0, which means we have no electrical current flow, then what happens is that this would be positive, this would be negative relative to a other circuit. So what would happen is this right here would cause the current in the circuit to flow one direction, then it drops down to 0, and then what does it do? It reverses. So AC, the electrical current flow in the circuit, is constantly doing what? Well, back and forth, back and forth, back and forth, back and forth, back and forth. It's constantly changing direction. And there's a reason for that you'll learn while you go through your studies. And these things here, they're just constant repetitions of each other. Well, what we do is we come up here and we identify one repetition. So this would be one repetition. So that would be one repetition of a repetitive waveform. And we refer to that. Anybody know what that's called? Some of y'all got to know this. So Christine's got an excuse not to know it. What's one repetition of a repetitive waveform? Anybody know? It's called a cycle, which is basically, we see cycles all the time. So let's call the cycle. And then we have what we call the rate of the cycles. The rate of the cycles are what we refer to as frequency. So frequency is the rate of the cycles of a repetitive waveform. In cycles per second. Now, what's happened is that cycles per second, Rich, CPS, is that usually when people come up with things or they're fundamental in the development of a science, they get the honor of their name being used. So Hertz is the last name of one of the persons that were fundamental in the direction of the study of electricity. So he had the honor of his name standing for cycles per second. So Alabama Power generates 60 hertz, which means what? 60 cycles per second. We get one cycle every 16.6666 milliseconds. So for 2,000 cycles, we can hear frequencies are different for different people, but usually around 20 hertz, you can start picking up your bass. And then we usually round off around 15 kilohertz. That's the sound vibrations that we can hear. So that's what your ears are doing. So it's responding to these waves, and then of course it's causing your little eardrum in there to do what? Move. And then you got that little old wishbone in there that's got a sensor on it that's converting it into what? Electrical impulses and sending those pulses to your brain. So your brain can't hear, but it's got a section in your brain that processes sound. So it picks up those pulses coming from that sensor, right? You understand that now is AC, or alternating current, and it goes into your brain, and now your brain says, okay, that's 60 hertz, and 60 hertz sounds like this. So we think we're hearing, but it's actually our brain making us think we hear, right? You understand? Which is really, really cool. So we hear that like you hear off transformers. That's why transformers hum at you, because they got 60 cycle on it. So they're up there vibrating. They're vibrating at a frequency that we can hear. It's well within our hearing range. Y'all ever heard of a transformer buzz? Out there? That's what you're hearing, 60 hertz. But we get up to 20,000 or 20 kilohertz, then we can't hear this anymore. So you can't hear these ultrasonics. But what they do is just like here, you can hear in this room, when I talk, you can hear there's an echo because the room is big enough. So what's happening is when I talk, can y'all hear the echo? Can you hear my echo? What's happening?
Sound bouncing off the
So I'm sending out sound waves and then they're bouncing back. And if I could measure by the time that I go like that and how long it takes to go back, that would give me sounds travels at, what's the speed of sound, 720 feet per second or something like that. That would come up, or 722, I don't know. It's fast. Feet per second, not miles per hour, feet per second. Then what can I do? I can get a distance out of that, and now you know what an ultrasonic sensor is. So an ultrasonic sensor, what it'll do is it'll send out these waves, and what does it do? It just times how long it takes for that thing to get back. Then it knows what? It knows distance. The only problem we got to worry about is, how much absorption does what it bounce off. It works real well. So distance is the amount of space between two things. A level is the amount of vertical distance or height from a ground or another stated or understood base. So level, we're talking this, right? So level, we're talking about vertical. Distance, we're talking about anywhere, up, down, sideways, or anything like that. Are we okay? Ultrasonic waves into electrical signals or vice versa measures time interval between the sending and receiving the watch. Echo. By the way, these devices, and you'll hear this term right here called a transceiver. What do you think a transceiver is? Right there, it's at the sound. It's a combination of what? Both of what? Yeah, transmitter and a receiver. So your telephone is a transceiver. So not only can you do what? Not only you can talk, you can send information, but you can also what? Receive it. And it's inside one unit. Now, the sensors are going to fall into two types of categories. We got what we call digital, and then we got what we call analog. Which one is more precise?
Analog?
Analog. Most people want to say digital because we live in a digital world. So digital, what it does, it deals basically with two states. We call them true, we call them false, we call them yes, we call them no, we call them on, we call them off, and of course the world famous 0 and 1. A lot of your off on buttons are like that now, which is a 0, 1. They just put the 1 inside the 0, right? You ever seen an off on button like that? Yeah, I'm sure you have. Most of your TV on and off buttons are like that. So what advantage does digital have over analog? Analog is something that's continuously has the ability to continuously vary. So basically, if I had 2 points and it was analog, I could literally vary in an infinite number of combinations between maximum and minimum. It's like the temperature. How many? So we say the high today is going to be 96 degrees. The low tonight is going to be 83. How many different temperatures is it between 83 and 93? We jump it down in degrees, but then there's actually small units like that. So temperature change is an analog value. Speed is an analog value. So basically, when you hit the gas on your car, you're going from 0 up to some speed. Actually, there's an infinite number of variations of speed up through what minimum to maximum. Even though we call it miles per hour, there is literally an infinite number of variations.
So what would you say is the easiest way to describe the digital and analog?
Digital and analog basically deals with 2 states. So that means I'm going to represent digital. In electricity, we got 3 things that we got that we talk about all the time. We got voltage, and we got current, and then we got resistance. But this is not, we can't transmit resistance. So it means if I can send information, I can either send it with a current, right? But you can't have current without voltage. So the primary way that we send information is with voltage. So if I'm going to send digital information, we could say, okay, plus 5 volts equals to a 1, and ground or common or 0 volts equals to a 0. So now I can send information just using 1s and 0s, right? You understand? So now we can represent digital extremely easy with electrical quantities. So some things, if I want to know if something's at a certain spot, then digital would be the route to go. I'm going to say, okay, it's either there or it's not there. So a lot of your sensors are digital sensors. We're just trying to say, okay, is it there or is it not there, right? You understand? Is it above this weight or is it below this weight? So we can set what we call thresholds. So if it's above 100 pounds, it's true. If it's below 100 pounds, it's false. We can store it real easy because all we're trying to store now is 2 voltage levels. I'm trying to store a 0 or a 1. right? You understand that? So we can store it. The circuitry that processes, the microprocessors that process digital information are relatively simple compared to me trying to deal with something that's constantly changing, which is analog. And the technique we talk about is, and this is, I've got a flashlight and I'm across the campus over there and I'm trying to send you a decimal number, 0 through 9. And what I'm doing is I'm using different light intensities, and each one of those light intensities represents one of the numbers of the decimal number system. And you're trying to write these down. Okay, you're sending me a 9, you're sending me an 8, you're sending, right? Or I'm trying to send you the letter of alphabet, and 26 characters, and I'm trying to use different light intensities to send you those. So I'm trying to send you 26 light combinations. What would be the odds of you receiving them right? Slim to none, right? But how far could I get away and you tell if the flashlight was on or off? As long as you could see me, you could tell if the light was on or off. So if I could come up with some flashing pattern and each pattern represents a different letter, then of course the Morse code is something similar to that, right? They used a symbol of dots and dashes, but you wasn't trying to tell. I wasn't trying to send you an intensity for a letter A. I was sending you a digital pattern, either the light was on or off, and now I can send you information over a long distance. All you got to do is have the ability to see the light. So one of the big advantages of digital is I can transmit it and I can receive it with very little error. So instead of being 5 volts, I can say, well, what if I let it go between a range, between like 2 volts up to 5 volts, and I'm not trying to get exactly 0 volts. I might be able to get like a little minus voltage or a little plus voltage, and anything that's within that range is considered to be good. And now we can send information over long distances, right? You understand? So here's my network cable right here. Is this analog or is this digital? No, it's digital. Ones and zeros. That's all it is. Because I'm trying to transmit this up to that thing up there, and then I'm trying to take that and transmit that over that orange cable, which is fiber optics, all the way up to building A. And then it leaves building A and goes out through what they call a T3 line and goes over to the Birmingham campus. Now, what would be the odds of me getting a voltage level all the way over to the Birmingham campus? Well, it'd be just pulses. They're just sending pulses over there. It'd be okay, right? You understand that? So one of the biggest advantages of digital is we can transmit it easily. We can store it easily. You know, we can save it. You know, DVD is nothing but they call pits and lands. It's just a bunch of little tiny dots in there, and your DVD player is reading those dots, and then by reflection. So basically, a pit would be something like this, and then a land would be something up there. And I'm shining a laser light like this, and I'm bouncing it back into a receiver. Well, what happens is when it hits up here on the land, it'll bounce back. If it goes down into the pit, it reverses back in a different angle. And now all of a sudden I can store ones and zeros on a DVD. Up 4 gigabytes of information on a surface. And of course, some DVDs you can flip them around, right? I haven't seen a double-sided DVD reader yet, even though I'm sure they're out there. But yours is a single-sided reader. So you got some DVDs you go out there, and one side might have high definition, the other side might be low definition. You just flip it around. But all it is a series of digital pulses that come in. And sooner or later is converted to analog. Analog, though, has the ability to deal with infinity. So my eyes are not digital. My eyes are what? Analog. So my rods and my cones are taking that light in those different colors and then sending a proportional electrical signal to my brain, and my brain is processing that as red. So we don't actually see red. It's an interpretation that our brain comes up with that makes us see red. And some people have problems with that. Some people's brains don't interpret that exactly right, and we have people, we call them colorblind. They cannot see certain colors. But they're seeing the same thing you're seeing. Why ain't they seeing red? Because their brain the programming in their brain is off just a little bit. Anybody in here colorblind? Yeah, red green is one of the main ones, and they'll see like brown. It's a problem in electronics because we use color code all the time. Yeah, residential wiring is no big deal because residential wiring we only have basically 4 colors. Commercial wiring though, that's where they start running into individual strands, and every color wire means something. So we have analog sensors and we have digital sensors. Most of our digital sensors are really analog sensors, but they run through something called a to D converter. And what we do on these is we can set what we call a threshold on them. So if it exceeds the threshold, the sensor sends back a 1. If it don't exceed the threshold, the sensor sends back a 0. But the actual sensing element is actually an analog sensor. Analog to digital converter. Plan ahead, right? Converter. I hope it says converter. Yeah, it converts an analog signal into a proportional digital. Usually if it's a digital signal, then it's what we have the ability to do, and we'll look at this when we go over there. If you look on the sensors, just about all of them has a little screwdriver setting in there. So what you can do is you can go on that screwdriver and you can set what we call the threshold. And what you're doing is you're saying, okay, if it's above this threshold, I'm going to send my computer a 1 or a voltage. We say a 1, but actually all it's doing is sending out a voltage. And now we took a physical stimulus and converted it over to a voltage. Now I can send that into a computer. Now computers are digital, so they love digital sensors. If I'm going to use an analog sensor, then I've got to have a watt out there. Yeah, I got to have an ADC out there and convert the analog signal into digital before the computer can even deal with it. So when you buy programmable logic controllers, this is what you have to specify. You have to get. We'll look at the little segments. We got an analog port on that, which is pretty neat. So an ultrasonic sensor can either be an analog ultrasonic sensor or a digital ultrasonic sensor. So the one that we have over there is digital. But the actual sensing element on both of them would be the same. It's just that one of them we run it through an A to D converter inside the sensor. The other one we would send it as a DC level representative. Are we okay? Yes, no? So ultrasonic sensors can be designed to detect distance. They can be designed to detect movement. They can be designed to detect level. Y'all understand the difference between distance and level?
Yes.
So level is a vertical measurement, right? You understand? So when you're down there in Pelham and you see the big tank farm over there with all that gasoline in it, what do you think they use to detect the level? They use ultrasonic sensors. They're actually in the top of the tank, And that's the way they measure the level of the fluid inside. We can use it of solids or liquids. We can use them to measure speed. So ultrasonics and radar is a step above ultrasonics, but it uses the same principle. So how does we call them radar guns? How do they work? Yeah, that's what it does. It measures how fast it covers a certain distance, right? You understand? So it shoots out one beam, measures that, then it shoots out another one, then the time it reflects back, it comes back and calculates the speed. Some of them, by the way, are going to ultrasonics because they don't put out as much electromagnetic energy that these radar detectors can detect. Now, the only limited they have is, of course, by the shape of the surface and the density of the surface. So this is what a bunch of our airplanes are trying to do now to prevent them from bouncing off these waves. So they have all types of shapes. They got, I think the B-1 bomber has a reflection of about that of a bird, I think. Ultrasonic distance sensors. Of course, this is one that they use. They use this for women that's pregnant and expecting a baby, but they also used it. They use it on me when I was in the hospital. I laid on my back so much that they'd bring one of these things and they'd look for blood clots. They'd run up and down my legs looking for blood. I was on a lot of blood thinner. It was pretty neat. This is basically kind of like the ones that we have over on the Amtro line. Bulkhead mounted or whatever will, and of course the transmitter and receiver on one unit. So this would be analog. You ever seen those pictures? Baby in the womb, man, that is so cool. And you say, I hope they don't look like that when they're born. But it amazes me what they can do with this. So they use them, like I said, they'll run them up and down my legs, down the main arteries of my legs, looking for blood clots. Yeah, if you lay on your back a long time, that's one of the big concerns they have is you're developing blood clots. Well, then when you start standing up, your feet really hurt because your feet's not used to getting that blood flow. This is an ultrasonic sensor. It's just that you can actually see the two heads on it. Yeah, one of them's transmitter, one of them's receiver. So this is basically the ultrasonic sensor that we have with the Lego robot, which is pretty neat because they look like two eyes. So I think I showed y'all my robot the first day of class, that maze solving robot that was coming up here. It was swinging that thing around, and it looked like it was looking around. Well, basically it was, but it was using ultrasonics. And it was using an analog sensor. And what it was doing, it was trying to see which one had the clearest way to go. So that was a pretty neat program. I'll show you that when we get there. But that sensor looks almost just like this, but they've got it inside a plastic cup. So it looks like two eyes. I did see that, right? You want to go get it? That's because you only have one sensor. So if you only got one sensor that senses the line, you can't sense the width of the line, right? You understand that? So what you'll do is you'll write it so when it sees white, it'll turn one way. When it sees gray, it'll turn the other, and it follows the side of the line. So you'll be using one of the light sensors. So that's ultrasonics, guys. You can see, like I said, and I'll show you all the program when we get into it. But I'll turn my camera toward it. So this is the one basically they're showing you on that is this guy right here. And what's neat about it, it looks like eyes. So you notice what the program does, if it picks up a reflection off ultrasonics, what did it do? It turned one way, and then it turned the other, and then it figured out which was the clearest direction, and then that's the way it turns. But you got to understand it's programming, right? It's programming. So that's ultrasonics. Maybe we'll show you how to program this, but then we got these other sensors down here that we'll talk about that basically can pick up things on the floor or on the side that the ultrasonic sensor just can't see.
So then what are they called? It's ultrasonic sensors. What are they?
These are called, in robotics, they usually call them tactical sensors, which we'll look at later on, but their devices we'll call limit switches, which basically these are definitely nothing but digital. So these are like the push buttons on these are exactly like the push button, the keys on your keyboard. Yeah, it's limit switch. What we're going to call, they're not even hooked up right now. They would actually come in right here. These are optical sensors, and we'll look at what type of optical sensors these are later on, because we got all these different types of sensors that we're going to look at. Right now, we're just talking about what? Ultrasonic or distance sensors. We're looking at distance. So ultrasonics is one of your main distance sensors. So this is ultrasonic. So what does it do? It sends out a wave, and then it times how long it takes for it to bounce off the object. We can use, and I don't know if the book covers this real well, but we could also do the same feature with photoelectric. So photoelectric, these are sensors that use light. And what can we do with light? Well, light does a lot like what sound does, right? You understand? So light reflects off things of certain colors. This is one advantage that ultrasonics has. Ultrasonics is don't worry about color. All it's worried about is just how dense the object is. So the less dense the object is, the less we'll get back, right? You understand? But the timing is still there. Y'all understand? So it's how much, the less dense it has, the more absorbent it becomes. And that's basically what they are treating these airplanes are. They don't say they don't show up to radar. They say they decrease what they call their cross-sectional area, so they don't look like airplanes anymore. They say that I think the B-1 reflects back like a bird, but there's not many birds that can fly at the speed of sound. So what we do on triangulation is we transmit at an angle, and then we measure the angle of the reflected light to determine the distance. This is called triangulation. And the other method we use photoelectric is that we send out a beam of light, and then or a pulse of light. So they send out a pulse, and then they measure the amount of time, the sensor would measure the amount of time that it takes to reflect back. So these are called time of flight sensors. So triangulation would be like this. So what it's got, it shoots out a beam, it reflects off the surface, then it comes up here and hits these different photo detectors. And depending on which photo detector would indicate a what? A distance. And these are called triangulation photoelectrics. You understand that? Pretty straightforward. And this is almost identical to ultrasonics. We call them time of flight photoelectric distance sensors. But basically it sends out a light pulse, then it measures how long it reflects back, and then it can use that to calculate distance. We don't have any of these over here. Only distance sensor that we have is the ultrasonic. Okay, any questions there? Okay, guys, y'all go ahead and take a break. Another break. Let's take about 10 minutes, and then we'll go up. Guys, I don't know what to do about that. I sent out texts, sent out messages. They sent out emails saying if your class, our class runs long, right? You understand that? Unfortunately, when they send out email, they are academic people, so they have these 1-hour academic classes on their mind, and not these 5-hour classes. So that's why I sent y'all out. I tried to send y'all out a text.
I think it was pretty clear that we needed to be here today.
Yeah.
But,
We'll redo it. Let y'all turn it in Thursday. But that's it. If they don't do it on Thursday, I'm not going to take it after that.
what, research?
Yeah.
I just want to make that essentially.
Really no great.
Still working on it.
I think Gary turned his last week, I think. Yeah. The time of flight and triangulation, y'all okay on those different types of photoelectric sensors? I need to put those in the glossary. Like I said, I'm working on a glossary. There's a section in the glossary. So what I'm doing with the glossary, I'm setting it up into different sections depending on the lecture. So I got one section on robots, and I got one section on sensors. And then there's another section, I think, on fluid power, even though sometimes we get the fluid power, sometimes we don't. Ultrasonic level detectors should make pretty good sense here, right? If it can sense distance, then it can sense level. Are we okay? Yes? Nope. Liquid level sensors, we have what we call discrete. These are going to be digital. And then we have continuous level detectors. So these will be analog. If I understand the difference, yes or no? So these are discrete. So the one in your commode is a discrete level detector. So what happens when you flush your commode? Most of you have tanks in y'all's commodes, right? Some of them use timers. Most of you have tanks. So when you flush it, it goes down, and then it's got a discrete level detector in there. It's just a float that when your water in your tank gets up to a certain level, it cuts off the valve. Oh yeah, that's why we talk about the ones. That's what I showed. That's what I told y'all. Well, this is what they use in the gas tank farm down in Pelham down there. You can see from the interstate. They still have float. Yeah, but if it leaked, they were pretty good at it, but cars still use floats. They still use floats. So the floats have been used in cars for years. And so it takes a level in your automobile, but that's what we would call a continuous level detector, right? So we have a device called a limit switch. A limit switch is a device, it's basically a switch. But it's like your wall switch over there. We could make the wall switch into a limit switch. Just taking some type of operator and putting it out there when you walk by it, turn it on, when you went back the other way, it would turn it off. And that's basically what a limit switch is. A limit switch is usually spring loaded, and then it's got what we call an operator on it, some type of operator. And so what they got on this, they got a cam. And when the float gets up to a certain place, it rides over that thing and turns it off. Y'all got an ice maker in your car? I mean, in your refrigerator? Well, it's almost this exact thing. So you got that little wiper that when it raises it disables the limit switch, and when you feed ice of it, the level drops down, and that metal wire drops down and does what? Tells it to feed more water or go out and do your ice. It tells it to feed the ice or to eject the ice, and then everything after that is timed. They had photoelectric. One of the big storage things they had out at U.S. Steel used photoelectric sensors. So what they're doing is they're shooting a beam through it, and of course when the liquid gets up, what does it do? It breaks the beam. And when it gets down to a certain level, now it can go through it, right? Y'all see that? This is what they call a resistive probe. This is actually an analog device. So up in here, they would have to have an AD converter. And what happens is that when the water gets up between these two electrodes, then these guys right here basically just measures the resistance of the liquid. Are we okay? Yes or no? These would be analog. So this is using a device called a potentiometer. Y'all had these things in EET 100 yet?
What's that?
Potentiometer.
No.
What a potentiometer does is, if we drew the symbol for it, this is a symbol for a resistor. And then what we would do is we'd come over here and we put this thing right here coming into the side. We refer to this as the wiper. And then what we do is we put a voltage across here. Let's say 10 volts. And then what we're trying to measure is actually this guy right here is going to move this wiper up and down. But what it does is that it gives you a voltage that's proportional to its position. So if this was a 10K pot and we had it set up like this, where the wiper gave us 5K up here, 5K right here, and if I measured the voltage at that point, this would measure 5 volts. So where we move, so the further it moves up this side, it moves toward 10 volts. The further it moves down to this side, it goes, if I make this my common, then it moves towards 0. So basically we could get any voltage out of this thing between what? Between 5 volts and 0 volts. And then the voltage that we get out would represent something, right? You understand that? So what's happening here is they've got the weight, but they got the float, and then when the float rises, this weight pulls this down, this turns the pot right here, and then what does that do? That changes this guy right here, which gives us a different voltage.
If it's 10 volts at the very top,
yeah,
and then it goes down, it cuts it off.
It gives you 0 volts out.
Yeah,
The power supply or the DC voltage source sees 10K. It don't see anything else. What we're doing is going out to our controller would be a voltage between 10 and 0 volts.
but the main thing is, you get your flow across there, that first one,
Yeah, maximum would be 10. Minimum would be 0. Maximum would be 10. I think there was a question like this on the So this is a potentiometer. It's hard to turn without a wiper. Without a knob. This is a potentiometer. This is a rotary potentiometer, which is the one they're showing over here. And what we'll do across the two outside leads, this is where we would put our DC voltage source. So 10 volts. And then what happens is we establish one side is common, and this right here goes to what we call the wiper. And as this turns, what I would do is I would get a voltage out of it that represents the position of this knob here, which is pretty neat. We had a guy that, I didn't bring him out, the yellow robots, he literally came out and put pots, so it's an open loop robot, but he came out and put potentiometers on every axis and then run that into a controller, a Arduino microcontroller, and now he had a closed loop robot. Because when that robot turned, it turned a pot, and then it gave a voltage out that was proportional to the watt, to the actual position of the robot. So it became now it's closed loop, so now it became very precise. And when y'all do the lab, when y'all do y'all's online programming of this robot right here, it's open loop and it runs off batteries. So if my power source is constant, then these guys here are really, really active. If your power supply changes, yeah, 4 batteries, but it only uses 2 at any one time. So it's only using 3 volts, because what we do to change the direction of the motor, you have to change the polarity, and y'all not going in there and swapping the battery. So what it does is it oh my goodness. So what it does is it comes up here and it's got 2 cells, and then it's got 2 cells right here, and then this right here is the common. And then what you're doing with those little rocker switches, so here's the motor out here, and what you're doing with those rocker switches is you're either switching it to this side or you're switching it to that side. So that's why the motor runs at watt. Either direction. So those are little 3 volt motors. So you can't control the speed. We've been thinking about actually putting a microcontroller on it. Yeah, so if I switch to this side, this would put a positive and the current flow would flow this direction to the motor. If I flip it to this side, then this is minus and it would flow to this direction of the motor. Since I changed the direction of the current flow to the DC motor, then it would do what? Change directions. And that's all you're doing when you push those switches up one way or down one way, is this is exactly it. What are they doing here? What they're doing here is they're measuring what? Pressure. Here they're measuring weight. Here they're measuring resistance, and here they're using ultrasonics. So we have quite a few of different analog or continuous level sensors, and we have different position sensors too. We have position sensors Position sensors are looking for something over a range, right? You understand? So position sensors have to be analog, where a distance sensor might be digital, but if it's digital, it's going to trip at a certain distance, right? You understand? Like on your commode. So when you flush it, all it knows is, hey, I'm below this level. You don't know what level it's at. All it knows is below the level, and then it turns on the water and starts filling up, and then it stops when it gets up to a level, right? It has no idea what level it is between down here and up there. It has no idea. But digital, it don't matter. But over here on this tank that's up on the hill that we have, they need to know how much water is in that tank. So they have an analog detector on it. And used to, they had a gauge on the side where you could actually see when it was full, kind of like on your car. You need to know how much gas you got in your car. Now you got two types of level sensors in your car. You have a digital. Now most cars have digital and they have what? Analog. Well, basically it's analog, but it's just got an A to D converter inside your engine control module your body control module that has a threshold built in it. And if it gets below that threshold, it turns on a light that says you need to put water in your car. You need to put fuel. If it's below that, yeah, you have an ADC, but it's usually not even out there on the sensor. It's inside the body control module. Used to, we had control modules that handled everything, but now cars are so complex, it usually has two computers in there. It has one that runs the engine, and it's got one that controls everything that goes on in the body. So how long your radio plays, and how long does it wait to lock your doors, and all the burglar alarms and stuff like that would be part of the body control. So guys, we're still got a lab. We need to do the lab on where y'all do the offline programming for this robot. Y'all gonna do online programming for this robot. This robot right here is offline programmed, but it's having all kind of problems. For some reason, it's picking random programs to run. It'll just take off on itself. So I got to figure out what's going on there. So we'll give y'all an extension on the homework lab. We'll give y'all to Thursday since most people are absent, and there will be no grace period. So if you don't turn it in Thursday, then we're going to stand up and you just kind of tell your class what you found. You're going to do that too. I think that's in the lab, right? That you're going to have to do that.
It says you need to do that, and then the bottom says you don't need to do that.
Oh.
It's up to you.
I guess it is. Most things are, right? Like we were going to be in lab today after we reviewed what we went over last week. Well, we're going to be in lab all day. But I figured out it was going to be a waste of time because most of y'all's team members, we don't ever have to make it. What we end up with, it depends on how fast you are. So when you start putting the Lego robot together, some people have a lot of time to practice with it, and some of you don't. But everybody gets through with it. Everybody that I remember gets through with building, but competing, that's where we start having problems. Or prizing problems. We got prizes to do that. So we'll compete our Lego robot. We'll put a path over here, a line you try to figure out. We got a name set up. We got a driving range. Drive. Yeah. You're getting the same. Okay, guys. See y'all Thursday. You're doing about the same thing that Nancy. But Nancy had to have it done twice. Her first one didn't work.
Well, he said he didn't get the camera on it. You know, I'm going to say, 25 years ago, I was on a plane going to California, and the guy took the time and invented something. He was telling me back then, he had invented a system.
He did. He invented a type of thing.
Yeah, a system. What it was, through pipe flow of cold slurry, he could tell you how much sulfur was in the coal.
My wife said, Nancy wants me to call her as soon as possible. No rest for the weary. If I tell you.
Evan?
Hey, what you mean? No, I haven't.
Pretty good, though, I think. First look at that. Okay.
I will. I have heard.
You didn't get one?
Gang and wide. The first order. Well, that forward, that's first order for the ECI stuff. No, but that's where we all my wife is taking
Has to be done by Thursday.
Yeah, it's supposed to. Okay. I got time.
a lot of that's pretty good. I don't know. She said I'm at Middle Creek. Ugh, what she said. Yeah, I got it. Well,
Well, the bill.
Wow.
Yep. Matter of fact, I still own some land down there. If you go across the bridge, it's 7 miles.
I think probably. There you were on wind, sir.
That's a wolf.
Sorry about wrong.
I got that. I got it.
Yeah. Okay. I'm gonna go call my wife. I'll just have to wait.
I just gotta get gotta get more value out of that thumb drive. I can get that.
No, he was.
Or what? Alright. Wow, I might be wrong. I just read it. You have another copy of the homework file. I never did get one. I didn't get one. When I asked that book, cleaned up all over the place. Supposed to have. I remember asking for one last time I was here, but someone told me it's going to be given out next week.
Oh, yeah.
Yes. Well, I mean, that's what I asked. I tried to get one.
Yeah, we get to clean up the whole lab last week. That took up part 6. We got this from
Well, I guess you don't have.
See better?
Sure. It's like this.
I'll grab it.
Okay, good.
I'll grab it.
But they got them up there. It's full of
Yeah,
stuff. Right.
like a thumb drive. Plug in the USB port on your PC. That's what it means, right?
Where I had one. I need to.
I got this.
Okay, this backpack. They used to have to see what you look at.
I don't have any idea how long I've had mine. The one I carry my, yeah, we got one of those too, but we don't.
That's the handle I got.